Hello everyone, welcome to this lecture number 7 of the NPTEL lecture on charging infrastructure. Let us discuss in this lecture diode bridge rectifier with capacitive filter, and in the previous lecture we have studied about the single phase full bridge rectifier, where the rectifier is also called as the full bridge uncontrolled rectifier, also. Now if we look very carefully, some of the inferences what we got was the output voltage is uncontrolled. That means it only depends upon the input AC voltage, or the whatever the AC voltage which has been applied, the output voltage is only dependent on that. You do not have any controlled variable with which you can change the output voltage to the value which you desire or which you want. Then we have also seen that since it is this rectifier is supplying to the resistive load, we have seen that the input current is sinusoidal in nature, and in this particular rectifier both the positive half cycle, where in the positive half cycle D1 and D4 was conducting, in negative half cycle D2 and D3 is conducting. In both the positive and negative half cycle, the power can be delivered to the output resistive load. That means in both the cycles the current will be drawn from this AC source, and we have also seen that the output voltage is the rectified DC voltage. That means it is not constant, it is continuously varying between 0 to the peak value and then again coming back to 0, and this is one of the problem, because the output is having the kind of quite varying voltage. So in order to restrict that, or in order to address that problem, generally the capacitive filters are used. Let us revisit the concept related to the single phase full bridge rectifier with capacitive filter. Let us revisit some of the concepts of this particular circuit, and because that will help us to logically develop the converter which are being useful in AC/DC part of the power conversion unit of an EV charger. So let us draw that circuit. So it has again the same 4 diodes connected in a full bridge manner and having an input voltage, input AC voltage which is been applied, then omega t, D1, D2, D3, D4, and then at the output it is not directly, it is been connected to the resistance. However, there is a capacitive filter also which is been connected, and then this particular thing will be connected to the load, resistive load RL. And let us define some of the currents. Now this one is nothing but IL current which is going. So this is the ID which is going into the which is the output of this diode bridge converter, and then after this you will have, there will be a current which is, some current will be going through this capacitor bank, and the remaining current will be going through this load resistance which is RL. Let us define this capacitance value as C, and the current which is going through this as IC. So in this particular manner the current will be going through this, and the voltage, let us define this particular voltage as VD, as we have mentioned in the previous converter as well. Now let us draw the critical voltages and current, some critical waveform in this circuit to understand the functionality of the circuit. So let me draw this. Let us first draw the Vs, Vs input voltage. So it has the sinusoidal variation goes in respect to t. Now this is my Vs, and this value, peak value, is Vs peak value. Now let us see how the output voltage will or VD voltage which will look like, because in this particular thing, since we have a capacitor which can store or which can hold the voltage across it. So this, let us see what will be my, or what will be the VD look like, how the VD will look like. So for that, let us draw the VD, how it looks like, to understand. In VD, what happens is that, assume the capacitor was holding a certain voltage, and this one, since this they were holding the voltage, and this voltage of the capacitor is greater than the voltage which is been applied, which is been there from the Vs, which is greater than the input voltage. So what will happen is that the diode D1 here, diode D1, D4, D3, D2, all will be reverse bias. Since all the 4 will be reverse biased, this load RL will be actually getting, or will be getting current from the capacitor, because capacitor, as capacitor will be discharging, as a result of it capacitor voltage will be falling down, because since there is no diode which is been in which is been forward, which is forward bias, all the 4 diodes are reverse bias. So the entire uh, power which this resistive load demands, or the current which the resistive load demand is been taken by the capacitor, and as a result of which capacitor voltage get discharged. So that is why it discharged from a certain value to its value at the point where this Vs will become equal to this voltage Vd. At that point, after that point, this Vs will be greater than, at this point Vs will be greater than Vd, and at that point where the Vs is greater than Vd, this D1 will be forward bias, because here you have a Vd. If you take this circuit, this particular circuit, in this particular circuit, this Vd will be, now the anode will have more voltage as compared to this point, as compared to the cathode, as a result of which D1 is forward biased. Similarly here, if you take the entire KVL, D4 will be the one which will be forward biased, as a result of which this D1 and D4 starts conducting, and there will be current drawn from this source. So as a since there is the current drawn from the source, the capacitor will get charged up, and as a result of which capacitor gets charged up, your VD voltage will rise. Further it will rise, and it will rise until this VD voltage will again become greater than this Vs sin omega, Vs peak sin omega t, and again at that point D1 and D4 get reverse bias, and D2 and D3 is already reverse bias, as a result of which the load will get power from this capacitor by, and I mean the capacitor will get discharged, and it will supply the required current or the power to the load. Hence you will see that the capacitor will be discharging, hence you will see that the capacitor will be discharging, and it will discharge until the next point where again this Vs will become greater than Vd, and at that point this D2 and D3 will get forward bias, and thus again the capacitor will get charged, and again at that point which is nearly at the peak, at that point of time the capacitor will be again discharging, goes till this point, again it will be charging up to the peak, and again it will be discharging, and again it will be charging, and then again it will discharge as it goes along. So the capacitor voltage will be having a certain ripple, however this ripple is much smaller than what we have when we do not have the capacitive filter, and the voltage, capacitor voltage, will vary between this Vd max and this point, which is Vd min. So the capacitor will be varying between Vd max and Vd min, and because of this let us draw the current which will be drawn from the, or let us first draw the ID current, and then we will draw the current which has been drawn from the input source and the current which has been taken from this diode. So let us draw what will be the ID current. Now ID current, as we see, from this point to this point it is the place where capacitor is discharging, so there will not be any ID current, only this capacitor will be actually be meeting this value IL. However, during this point to this point it is that time when there will be a current which will be drawn from this source, and that will be, we can let us draw that particular current. It will be of the shape something like, it suddenly goes up and then it will die down like this, and then again it will again start at this point, then again take up and then goes down. So it will have some peak value, and then again in the next cycle it will go up and comes down. Similarly here also it goes up and comes down. Why it comes down? Because after this point the diodes, all the 4 diodes get reverse bias, and then this capacitor will be then supplying this IL current. That is when the current drawn, I mean that is when the this ID current becomes 0. And if you see the IL current will be, so it is having this current which is been drawn is not a pure DC, I mean it is not the constant DC current, there will be, there is some portion of the time where the peak current kind of thing, the peak current is been drawn, while other portion it is 0. So that is why this particular current will have the average value, and that average value is defined as IL, which is been going into the load. Now if you look very carefully, this particular current has the peak value. Let us define this peak value as Is peak, and this will have some non-zero value, or this you can say that some current which is been drawn from this source. Let us say the time from which it start is, let us say Ta, and the time it again goes down, let us say Tb. Similarly, if we see our Is current which is drawn from the source, if we try to see the Is current which is drawn from the source, it is again the same, goes here in positive half cycle, the value is nothing but Is peak, and in the negative half cycle, if you see in the negative half cycle, this D2 and D3 will be in conduction for this period of time, and as a result of which this will have a current of the same shape in the negative direction, and similarly in the next positive cycle have the current going like this, and negative cycle it will have the current going like this. And if we see, the amplitude of this one is nothing but same as ISP in the positive cycle. So what we see is that we have imposing this AC voltage Vs, which is a sinusoidal wave. However, the current which has been drawn from the source because of this capacitive filter is of a peaky nature, and it draws current near to the peak of the sine wave in the form of peaky nature, Now let us see some of the things what we see from here. From TA to TB period, the capacitor C is charging, while in the remaining period let us define this time from here to here as T. That's when from here to here it will be T by 2, where we can write T is nothing but 1 by Fs, which is nothing but 50 hertz, and we can also write omega, which is 2 pi Fs. It implies our omega t is nothing but 2 pi. That we can write. The same thing we have also written in the last class. So from TA to TB, the capacitor C is charging, while in the remaining portion of, we can say that in the remaining portion of T by 2, the capacitor is discharging. While giving a current to the load RL. So thus we can see that in this particular system, the capacitor is charging for some time and it is discharging for the remaining portion of time, and the capacitor voltage is varying between VD max and VD min. And generally most of the converters, we have some tolerance where we can allow this ripple across the capacitor, or this voltage variation across the capacitor. So thus if we want to make sure this ripple or the difference between the maximum VD maximum and VD min to be within a certain limit, we need to size our capacitor such that we will be in a position to satisfy some of the requirements of the some of the load requirements, that the voltages should be between within a certain limit. So we need to make sure, we cannot avoid the charging and discharging. So we need to make sure that charging and discharging happen in such a manner that the voltages of the capacitor is maintained between VD max and VD min, and we can define that that ripple or the difference between this VD max and VD min as one of the specification of the converter, and that is when we can able to calculate the value of capacitor. So let us see how we can design or we can evaluate this capacitance value. So we can say that in order to maintain the voltage between VD max and VD min, energy gained during charging must be equal to energy lost during discharging. Why? Because if you draw, if your voltages, if you draw the the voltages of this capacitor goes up, that means you are charging the capacitor. When it is going down, you are discharging capacitor. So if the amount of energy which goes in, which gets gained during charging, if it is equal to energy loss during discharging, then we can make sure the capacitor voltage is maintained between VD max and VD min. So, let us see, to maintain the voltage between VD max and VD min, how a capacitor can be sized. So, we have to evaluate the energies during charging and discharging. So, the energy gained during charging, that means the voltage goes from VD min to VD max, is nothing but is equals to half. Let us define C, capacitance value, VD max minus VD min. So, half C VD min square is the energy before the charging and half C VD square max is the energy after charging. So, this is the energy gained during the charging. Let us define this as the equation number 1, and let PL be the load power, or you can say that power delivered to the load. So, generally we define the power of the load in terms of kilowatt as well. So, let us define PL be the load power, or the power which is been delivered to the load. So, we can say that energy delivered to the load from capacitor, again during T by 2 period from this point to this point. So, which is during T by 2, we can say that, let us define this as ED is nothing but PL times T by 2 times, since the, if you look very carefully, since the energy or within this T by 2 period, it is within this period, and within this period the capacitor is discharging, that means delivering power to the load. So, that is why we have to also take the average value of that particular thing. So, this is the time between T by 2 minus this period, which is the difference between TA and TB. So, we can also define one term called as a TC. So, we can also define a term TC, let TC be TB minus TA, which is nothing but the time during which the capacitor is charging. Let us define this as a TC. So, we can write the energy delivered to the load during T2 time as nothing but the time period during which the energy is been discharging, which is T2 minus Tc in the whole T by 2 period. So, we can write this PL into T by 2 multiplied by 1 minus Tc by T by 2. This is my ED value, and this I can define as a equation number 2. So, thus in order to maintain the voltage between VD max and VD min, we need to make sure this EC is equal to ED. So, that is why we can make sure ED is equal to EC to ensure the capacitor voltage is between VD max and VD min. So, that implies you can write half C VD max square minus VD min square is equals to PL into T by 2 to 1 minus Tc by T by 2. So, in order to calculate the C value, let us rearrange this expression to obtain this value of C, which we can obtain as C is equals to 1 minus Tc by T by 2 multiplied by PL by VD max square minus VD min square times T. So, here we can also define one term, see this VD max square minus VD mean, we can write this VD max square my VD mean square as VD max plus VD mean multiplied by VD max minus VD mean. So, let us define this as 3, this as 4. Further, we can also define a term called V delta V naught, which is the ripple, voltage ripple on the output voltage, V delta VD max minus VD min. This is nothing but the output voltage ripple or the ripple on the DC output voltage. Similarly, we can also define the average value of the ripple, which is VD max plus VD min by 2 is nothing but the output voltage. So, this V naught is nothing but the nominal output DC voltage, nominal output DC voltage, and that we can put this expression in equation number 4, and that we will say VD max minus VD min square is nothing but 2 V naught times delta V naught. Let us define this 5 and substitute 5 in 3, we will get C nothing but 1 by Tc by T by 2 multiplied by PL divided by 2 V naught delta V naught, and T we can define it as 1 by Fs. So, this is the value of capacitance one need to put for the required ripple delta V naught. And if you look very carefully this particular thing, this PL will be the value given as one of the parameter defined in the load specification. V naught is again the required values or required is a thing which is be given in the specification, load specification. Delta V naught is again one more specification which will be given generally in the load as one of the load specification, which tells that this particular load can sustain or can withstand this much voltage ripple. So, that is why these 3 things are the values which is been given. However, this Fs is nothing but the 50 hertz value, it is because it is the as the supply voltage is at 50 hertz, if it is 60 hertz it will be a 60 hertz value. T by 2 is again we can easily calculate by T, we can easily calculate as 1 by Fs, and there we can calculate the T by 2. However, is the Tc. So, if we recall the Tc, which is nothing but our the time during which the capacitor gets charged. So, if we reduce this Tc and so if we reduce this Tc, the capacitance value go up in order to make sure, if we reduce this Tc in order to make sure to meet that delta V naught value, the capacitance value need to increase if we reduce the Tc. So, this is one of the understanding we can get from this particular expression. This Tc is something which you can define and then calculate capacitance according to this, that means the time for which you want the capacitor to be charged, that you can take as one of the design variable and you can calculate the capacitance value. Further, if you look very carefully, we have understood what is the value of capacitance. However, in order to select the capacitor, one need to define 3 things. One, obviously the capacitance value which we had derived in the previous section. Second, the voltage rating, which is the maximum voltage the capacitor can withstand, and generally we will select the capacitor slightly, we will provide a certain safety margin and then we will select the capacitor accordingly. For example, let us say if the it has to hold the voltage of 400 volt, then we will definitely choose a certain voltage more than that particular voltage. And more importantly, we also need to know what is the RMS current through the capacitor, because this RMS current is the one thing which will determine, this will determine the parallel connection in the capacitor bank. That means each capacitor will be defined with certain RMS current it can withstand. Obviously, it is determined by the amount of losses which is happening in the capacitor, I square R losses. So, one need to also calculate, or one need to also evaluate the RMS current which is going through the capacitor. So, in order to select the capacitor, you have to first you need to know the capacitance value, you need to know the maximum voltage it will see in while the circuit is in operation, and also you need to know how much RMS current will be flowing through the capacitor. Since we have already have this capacitance value as mentioned in this expression, and also the voltage rating. So, if we see the voltage rating, so this capacitor has to block the voltage which is going between VDC max, or it has to block, or it has to withstand the voltage which is going between VDC max and VDC min. So, the maximum voltage which it can withstand is nothing but the value VDC max or VD max, which is nothing but, you can say that, your nominal output DC voltage plus V naught plus delta V naught by 2. So, in this way one can select the capacitor. However, we have known this capacitance value. So, this voltage rating is also been defined. Now, we have to calculate the RMS current. Since we have come up with this capacitance value, we will see how to further select the proper capacitance, because we also have to define its the RMS current which is going through this, that we will see in the next lecture. Thank you for patiently listening to this particular lecture. Thank you.